So the last talk of this session and the workshop is by Yann.
Hello, everybody. Thank you for making it till the last talk. And thank you for the organizer for this very nice week. It was a very nice pleasure for me to come in the US for the first time and to meet you all. Thank you very much. So today we'll talk about some work I have done recently with very super cool collaborators in Europe, mainly Hamburg and also Tel Aviv. So I did my PhD in Hamburg, Daisy with Filippo and Geraldine, and now I'm doing my postdoc with Tomer. I started 1 year ago. So first, let me remind you what is a super cool first order phase transition. So basically, it's when you have a hierarchy between two scales. The first scale is a critical temperature, when the two minima coincide and below which the transition becomes energetically allowed. But then, when the temperature drops below, the universe becomes dominated by the vacuum energy difference of the transition, which means that the universe is vacuum dominated and inflates. It inflates till the temperature drops below the second scale, which is the nucleation temperature, which defines when the nucleation rate becomes larger than the expulsion rate, and the field tunnels form bubbles that expand and percolate the whole universe. Okay. So we define supercooling as the hierarchy between the critical and nucleation temperature. What kind of particle physics model can lead to supercooling? Most of the model in the literature of first order phase transition, in the high temperature expansion, you can write it as a polynomial function. Okay. On the left, here I plot the potential for different temperature above the critical temperature, at the critical temperature, below the critical temperature. On the right, I'm plotting the bounce action, which is kind of the free energy cost per unit of temperature to tunnel. And since the potential is a polynomial function, the bounce action is a power law of the temperature. Okay, power law there, power law there. Okay, so it evolves quite fast with the temperature. Okay, and when the bounce action drops below the critical value, tunneling takes place. Okay, and the exit point is very close to the true vacuum. There is a second class of model, which are nearly conformal model, which you cannot write as a polynomial function. They are nearly conformal, which means that the mass term here at zero temperature, which is T naught here, is for some reason it is zero. Okay, you have a flat direction, and spontaneous braking arise due to radiative correction. One loop, Coleman-Weinberg, if you want. Okay, so you have a logarithm here, and then when you write the bounce action, since you have a log here in the potential, you have a log in the bounce action. The bounce action decreases very slowly with temperature. It decreases like 1 over log to some power. Okay, so then if you want to cross the bounce action to tunnel, you need to go to much lower temperature. And this is what generates the hierarchy of scale typical of supercool phase transition. The logarithm in the Coleman-Weinberg generates the hierarchy of scales typical of supercooling. And if you plot the potential for different temperature, let's go to 10 to the minus 2 of hierarchies. This is the potential here. But when you read the bounce action, you see it's above the critical value. So you should not tunnel, right? But when you look at the potential, you say, oh, but I should tunnel here, right? So why? Actually, when you zoom very close to the origin, and you see there is a small barrier. And this small barrier is enough to delay the nucleation. And then you need to go to smaller value, 10 to the minus 4 here, to tunnel. And the exit point of tunneling it's not close to the true vacuum, instead it's close to the nucleation temperature. Remember, you have two scales, the critical temperature, the true vacuum if you want, and the nucleation temperature. And the tunneling event is only sensitive to the second scale, the lowest, which is the nucleation temperature. So during tunneling, you can forget about what happened close to the true vacuum. Instead, tunneling is only sensitive to what happened at the origin. first order model generating first order phase transition can be mapped into two parameters, as you know, alpha and beta. Alpha is the latent heat normalized in terms of the radiation energy density. And for supercooled phase transition, it is very large. Basically, it's given by the ratio of the two scales, TC over TU, to the power 4. Very strong phase transition. And the beta, which is the time variation, the derivative of the bound section, since the bound section evolves very slowly, logarithmically, beta over h is very small. So phase transition are very slow. So this is the take-home message. Supercooled phase transition arise in presence of flat directions or nearly flat direction. They are strong, large alpha, and they are slow, small beta. You can categorize, classify nearly conformal models in three categories. I have two axes. I have the strength of the coupling and the number of space-time dimensions. At d equal 4, you have the Coleman-Weinberg in the weakly coupled regimes, one loop radiative corrections for small coupling. In the strongly coupled regimes, you have the light dilatance line. And epsilon here is anomalous dimension of some operator. And when this one is small, the two models are equivalent at tree level. And for d equal 5, you have, if the fifth dimension is warped, you can also have a nearly conformal model, and which can be understood that those two are related by holography. Actually, they are not equivalent, because when you look at the potential here, you have a power 2, which generates a potential which is whose exponent is 2 epsilon, while here you have only 1 epsilon. So then it's not equivalent, because this one actually, for some choice of parameters, it can have a barrier at 0 temperature. So I don't know exactly why you lose the equivalence. It was just a comment. Okay, nice. Okay,
I can tell you after.
Okay, cool. We have some expert in the room who will tell us later. Thank you. Today I would like to tell you about cosmological implications of such supercooling. So it's well known since the so-called RS paper 2006 that supercooled phase transition generates the largest gravity wave ever. I mean, among all the models of first order phase transition, the strongest gravity wave signal is when you have supercooling. Why? Because for supercooled phase transition, you have large alpha, okay? And you have small beta. And the signal goes like 1 over beta squared. Y squared, 1 power for the size of the bubble, the second power for the time of emission, the time for the two bubbles to cross. So that's why you have large amplitude, large bubble that collide during a long time. Second cosmological implication is that the bubble walls are moving very fast at ultra-relativistic speed. And if you want to compute the Lorentz factor of the wall, you need to compute what are the interaction of the wall when they expand with the plasma. Okay. If you want to compute the Lorentz factor, you have to balance the driving force due to the delta P, due to the vacuum energy difference, the accelerating vacuum pressure, you balance it against the friction pressure. We need to compute the friction pressure. This has been started in 2017 at the perturbative level. And then it has been, we have explored, I mean, with other groups, we have explored beyond the perturbative level. We have recent all the perturbative orders doing a Supercooled summation, and we have found the same result as them. And then we have explored also what happened if the gauge coupling is larger than 4 pi. Basically, you have a strongly coupled regime, you have a confinement. So you maximize the interaction of the plasma with the wall. And we have found the same results as with the curve summation and as with perturbative level. So the three results agree. So it's fantastic because Botecker and Moore, they just did a very simplistic computation at the perturbative level. Actually, it was very predictive because it's the same result is obtained when you resum or when you go into the Boolean string description. So you interpret interaction of the plasma with the wall in terms of flux tubes. And this is the gamma factor of the wall that we have obtained. And you see, you can reach 10 to the 12 for the gamma factor. So it's very relativistic. You can see Isabel Garcia, the talk for novel results that go beyond that picture. And actually, there are still open questions because nobody yet managed to compute the friction pressure in a gauge invariant way. So there have been first attempts here that I think we should continue to get something which is gauge invariant, but it's not trivial because the wall breaks Lorentz. So you lose Lorentz invariance, and then you also lose gauge invariance. At least trivially, you lose gauge invariance. So you have to quantize the wall to recover the gauge degrees of freedom hidden inside the wall if you want to recover gauge invariance. So it's not trivial, and hopefully in the future someone will manage. The third cosmological implication of supercooling is dilution of relics, because you have this inflation stage. So you can dilute any relics which has been produced beforehand. And in this talk, I would like to focus on heavy thermal dark matter, to use the dilution to have dark matter beyond the so-called unitarity bound. As you know, thermal dark matter, its abundance is set by inverse cross-section in the standard freeze-out mechanism. And as you know, the cross-section cannot be arbitrarily large because particles, they have finite size set by their de Broglie wavelength. And as it has been shown 20 years ago, this inequality on the cross-section and the requirement to satisfy the observed density implies a bound, an upper bound on the mass of thermal dark matter of 100 TeV. But now, if you engineer some mechanism which dilutes the abundance of dark matter after freeze-out, so you introduce some 1/d with d large, then you push the upper bound, the mass, to further values. How do you get d? So d, you can, yes, there have been many work to get d. For instance, you can get d from a matter era, entropy injection after a matter era. You can have a second annihilation stage via bubble squeezing. If you want to know more, you should ask Puya. You can introduce other particles that participate into annihilating dark matter. You can make dark matter a bigger object so that the cross-section is enlarged. If you want to know more, you should ask Ofri. And today, I would like to focus on dilution using supercooled phase transition, using the inflation stage. This has been explored in this paper in the warp fifth dimension model, in this paper in the Coleman-Weinberg scenario, and in this paper in the light dilatant scenario, strongly coupled regime. But in those two papers, we point out an important effect which has been missed out in the strongly coupled regimes due to strong interaction between the plasma and the wall. And they drastically impact the factor D, the dark matter abundance. I will give more details soon. And this is connected to the fourth implication of supercooling, particle productions. So in the strongly coupled case, I will give more details soon. But before, I would like just to point out that even in the weakly coupled case, when you have small interaction, I mean, smaller than 4 pi interaction between plasma and the wall, you can also have particle production, as it has been pointed out in this paper. And as we point out in this paper, a phase transition at the weak scale, which means that the scalar field driving the phase transition has a mass of around 100 GeV, 1 TeV. This scalar, even though it's only 1 TeV, can decay into 2 particles of 10 to the 8 GeV, light particles that decay into 2 very heavy particles. How this is possible? Because Lorentz is broken by the wall boundary. So energy momentum conservation is not satisfied. So basically, when the scalar passes through the wall, it will be put off shell by the presence of the wall, and then it will be able to decay into whatever is allowed by the energy which is given by the wall. This optionless, basically, it's a momentum exchange. It comes from a momentum exchange between the wall and the light particle. And interestingly, not only the light particle can produce heavy particles, but these heavy particles has a huge momentum because it's produced by a wall which is moving with a large relativity factor. And we have computed the interaction of those particles with the plasma from electroweak epoch till today. And we have found that the energy loss is basically zero and still continue to propagate. So we can have heavy particles which are still warm today. Velocity at matter radiation equivalence around 10 to the minus 4, which is the upper bound due to current data. There is a third way you can produce particles. If you think about it, an expanding bubble wall contains an event horizon. It's like a black hole because the bubble wall is accelerating. And if you are accelerated observer, you see an event horizon. And I think there are many implications of this. So particle production is one. Then those bubbles, they can collide. And then you have shell of Unruh particles that collide with another shell of Unruh particles. If you compute the center of mass energy of this scattering, since you have a large gamma factor, maybe you can go up to the gut scale, even though the reading temperature after inflation was, I don't know, TeV scale. Maybe you can produce gravity waves. Maybe you can read the universe only with a vacuum bubble. So I think there are a lot of things to explore. And the last cosmological application of supercooling that I would like to discuss today is black hole production. How can you produce black hole? So for this, this comes from the fact that the phase transition is very slow. It's very slow. So the bound sections decrease very slowly with the temperature. And nucleation is supposed to take place when bound section crosses 140, right? Okay. But it's not exactly when it crosses 140. It's a stochastic event. So you play dice. You play dice with a distribution which peaks. The distribution peaks there, but it's not. But you have a distribution, so you have a width. So it means that nucleation is distributed in time. So end of inflation is distributed in time. And if end of inflation in each individual patches is distributed in time, it means that the rating temperature in each individual patches is also distributed. So we have contrast density of the rating temperature. And if the contrast density is order 1, you can form black hole. And if you look at the number of Hubble patches contained inside our causal patch, Hubble patches at the time of the electroweak phase transition, let's say there was electroweak phase transition, the number of those tiny, very tiny Hubble patches inside our causal sphere is like 10 to the 50. It's huge. You have a huge number of Hubble patches inside our causal cone. So if you want to satisfy the current observed dark matter abundance in terms of black hole, you just need to collapse a small fraction of them. Let's say, I think it's 10 to the 15. 10 to the 15 out of 10 to the 50. So even if the probability that a given Hubble patch to collapse into a black hole is small, you don't mind. You will anyway saturate the dark matter abundance in terms of black holes. Is what we show here in this plot. It's coming. In this plot, we show that if a given, this is very generic, if a given first order phase transition is slower than beta over h equal to 9, you produce too much black hole. So basically, this is excluded. This is bit average over amount of supercooling, and everything which is in blue is excluded. You produce too much black hole. This is all I wanted to say. This is the landscape of cosmological implications. And today, in the time that I have left, a very small time, I will just discuss, I'll just give more emphasis on the strongly coupled case and discuss what are this non-trivial interaction between the plasma and the wall when gauge coupling are larger than 4 pi. So we're talking about phase transition which are like QCD-like, leading to confinement, but with a period of supercooling. So we're talking about supercool confinement. And what is the implication on heavy dark matter? What is supercool confinement? So you know the super uncool confinement, which starts in 2020, various outbreak, and which leads to a long confinement stage, which ends by the vaccination. Okay? Supercool confinement is different because instead of having confinement during this period, you have confinement at the very end of an inflation stage. So that's the difference. So first, vacuum domination, inflation, and then confinement. Now let's think about what happened for the quarks. We have quark around, right? So let's follow the cosmological history of the quarks. So first you have, let's say, one quark, anti-quark. So during the inflation stage, they get diluted away, they get separated, distance increase between them. And then the strong sector confines there, and they form a hadron. And then if you want to compute the abundance of those hadrons, you should include the dilution factor, right, due to this period, ratio of temperatures to the cube because it's volumic dilution. But this is neglecting the interaction between those particles and the wall. Because in order to confine the quarks, they have to pass through the wall. They have to enter inside the wall. Inside the bubble, they will confine. So on this picture, on the left is outside the bubble. On the right is inside the bubble. And this dashed line is the bubble wall. So the quark, they enter the wall. And when they enter inside, they form a string because you enter the confined phase. And then the string has a huge energy because, as you know, the potential grows linearly with the distance. But the distance is very large. It's 1 over temperature. Remember the hierarchy of scales. It plays against you here. So this cannot happen. This costs too much energy. So instead, the flux tube, in order to minimize its energy, gets distorted. The flux tube wants to stay outside, where its energy is vanishing. So effectively, it is as if each quark interacts with the wall via string-mediated interaction. And as the quark continues entering, the string, when it becomes larger than inverse distance, inverse confining scale, it breaks. The string breaks, and you form a lot of hadrons. The number of hadrons will depend on the kinetic energy of the quarks, analog to what happened in collider. And if you want to conserve color, you need to eject 1 quark. Because here you form a color singlet inside. So you have to eject 1 quark. So you can call it color radiation, just an analog to Hawking evaporation. But we are interested in the impact on the abundance of dark matter. Dark matter in this picture is one of those hadrons. So first impact is that you have, for each quark that enters, you have many hadrons. So the naive dilution factor gets enhanced logarithmically by the string breaking. Why logarithmically? Because we computed on picture and we fit. And the second implication, the second consequences on the dark matter abundance is that the string fragments, they are formed in the string rest frame. But the string rest frame, one of the extremity, one of the endpoints of the string is attached to the wall. So basically, the string fragments, they will be boosted with respect to the plasma. So the string acts as a catapult. This is a catapult which propels the string fragments into the universe. And the momentum of those string fragments receives a gamma factor, the Lorentz factor of the whole. Remember, 10 to the 12, very large. So when it's scattered with someone in the plasma, the center of mass energy of the scattering is larger than the typical confining scale, which is written F here. So it means that you will produce an avalanche of particles. The scattering will be deeply inelastic. And those daughter particles will again scatter deeply inelastically until all the initial kinetic energy of the mother particle has been converted into rest mass energy of all the little daughter particles. So the enhancement is proportional to the Lorentz factor, 10 to the 12. So we have three factors that determine the dark matter abundance. Let's put it on a plot. Here's my last plot. This is amount of supercooling versus mass of dark matter. Here we choose mass of dark matter equal 4 pi f. Let's say it's a heavy variant. And this is in green what reproduces the correct dark matter abundance, assuming the naive dilution factor. Already you have dark matter beyond 100 TeV, so you satisfy dark matter, thermal dark matter beyond the unitarity bound. So you're happy, but now you should take into account what happened at the wall interface when the quark crossed the wall. So you have formation of a string, flux tube attached to the wall, which breaks, which add a logarithmic factor. And then you have a catapult, which add a gamma factor in the abundance, and you see that this drastically changed. So basically, you see that to satisfy the dark matter abundance, you need to increase the amount of supercooling, because so first you dilute, and then you produce. So if you want to keep the same density later, you need to dilute more, so you need to increase the amount of supercooling. This is the final result. And interestingly, for this point, the nucleation temperature is around QCD, and if you find a way to catalyze this phase transition, which is PeV phase transition, or 100 TeV phase transition with QCD, then you get a good prediction here. And here it's interesting because the kinetic energy of the quark is smaller than there would be bound state energy, so they cannot penetrate. It's analog to the supercool version of the squeeze-outs proposal of Puya. But we didn't explore more, so we don't know exactly what happened. What are the signatures? Basically, gravity waves. I mean, it's huge. So all the parameter space in blue for dark matter will be probed by, LISA, Decibo, ET, and but also gamma ray telescope. Maybe there is a reach there. And this is my conclusion. So supercool confinement. Take a message: flux tube dynamics at the wall boundary produce a lot of particles. Other consequences of supercooling. I've talked about the off-shell decay. Light particles that decay into very heavy particles, Unruh gradations, black hole formations. And if you want to know more about supercooling, I advise this chapter 6.4 in this book, Beyond the Standard Model Cocktail. So it's a book, 2,400 references. It's a review of numerous BSM topics to be available at Springer next October, but $200. Don't buy it, go on archive. Go on archive, download the free version. So we have a review of standard model elementary particles. What are the open problems, hierarchy problems, neutrino, flavor hierarchy problems, string CP. I'm not an expert on all those topics, so I did my best. But so I know you're expert on all those topics, but maybe it can be good as a reminder of what are the principal ideas, what are the main references. So this is standard model of cosmology, CC problem, Pargenis, dark matter, small scale puzzles, Hubble 21, thermal dark matter, freeze in, freeze out, WIMP, miracles, Sommerfeld effects, exceptions, self-interacting dark matter. First order phase transitions, so bubble nucleation, how to compute the tunneling rate, thick wall, thin wall, bonds, shooting methods, semi-analytical approach, very useful. How to compute the bubble wall velocity, how to compute the friction pressure, how to compute the gravity wave signal, for different sources, scalar waves, turbulence, sound waves, and this is a review of supercooling. And a gravity wave from cosmic strings, if you're interested. I mean, it's already well known from Valentin book, but here you have also like deviation from Nambu-Goto, particle productions, which change the spectrum of gravity waves. More details on global strings. And for these conferences, these are the topics of interest. So this one on cosmic strings, this one on first order phase transition. And here, in 2 minutes, if you go there, in 2 minutes, just using quadruple formula, you can compute gravity wave from first order phase transition, cosmic strings, local strings, global strings, and inflation in 2 minutes. Yeah, thank you for your attention.